Next speaker is Daisuke Kishimoto. Daisuke, so please go ahead.
Thank you. Thank you very much. Let me thank the organizers for giving me a chance to talk here. I'm very happy to be here. I think I first met Fred at his 60th birthday conference. There are two conferences in 2020 for his 60th birthday. And I met him at the second one. And after that, he came to Kyoto. And Fred and Sam came to Kyoto, and we had a nice time. And I think I met Fred. The last time I met Fred was 2020 at the conference on polyhedral product here in the field. And I went for dinner with Tony and Fred and Kathy, right? It was really nice dinner, especially because he was talking about his nice memories of Japan and Japanese algebraic topologists like Toda, Araki, Nishida, Kono, and it was very nice because I was able to know some of their secrets. And of course, I'm not going to talk about it. All right. Okay, so let's start. What I'm going to talk about is the very classic topic, Lefschetz fixed point theorem, but in a somewhat non-standard setting. And what I want to show in this talk is mainly the framework where we can play algebraic topology for non-compact manifold. Okay. So in general, non-compact manifolds can be very, very wild. So it doesn't make sense to build up theories for all non-compact manifolds. So we need to fix some a class of non-compact manifolds. And in this talk, I'm going to talk about, I'm going to play with the non-compact manifolds of bounded geometry. It is a Riemannian manifold whose injectivity radius is positive, and the curvature tensor and its derivatives are bounded. So, for example, if you have a covering over a closed manifold N, then if the fiber is infinite, M is non-compact, and the manifold M equipped with the metric, which is a lift of a metric of N, is a manifold of bounded geometry. Okay, so roughly, manifold, non-compact manifold of bounded geometry is a non-compact manifold which are not very wide. Okay, so we can. There are many interesting theories on non-compact manifolds of bounded geometry. For example, I think the most famous one is John Rowe's index theory. He built up his index theory for non-compact manifolds of bounded geometry, satisfying some additional conditions, which allows us to take a sort of average. Okay. Okay, so in this talk, actually, there are only a few results on non-compact manifolds of bounded geometry concerning which are analog to the classical theorem like Poincare-Hopf theorem and Lefschetz fixed point theorem. But we have the following nice theorem of Weinberger. So, right, so he considered a manifold of bounded geometry. And for a manifold of bounded geometry, we can define its Euler class in bounded cohomology. And he proved that there is a non-vanishing unit length vector field with bounded derivative. On M, if and only if the Euler class of M vanishes in bounded cohomology. Okay. All right, so, and of course we have to assume that the vector field, the length of vector fields is bounded, and also its derivative is bounded, because every connected non-compact manifold has non-vanishing vector field. Indeed, we have a vector field with isolated zeros. And if the manifold is not non-compact, we can sweep out zeros to infinity and then get the non-vanishing vector field. But yeah, the point here is that its derivative can be explored. So we have to assume something on the derivative. All right, so from this theorem, we can easily see the following corollary. M is a manifold of bounded geometry. Okay, so, so if the Euler class of M is non-zero in bounded cohomology, then any isomorphism of M, which is the one close to the identity map, must have a fixed point. Okay. And I want to generalize this corollary to a sort of Lefschetz fixed point theorem. To this end, we have to set up which self map we are going to deal with, and we have to set the right homotopes for it. Okay. And the Lefschetz fixed point theorem has several variants, and here I'm going to consider this fixed point theorem, Lefschetz fixed point theorem, which is due to Fadel. Okay, so of course he considered the closed manifold, compact manifold. Okay, so M is simply connected closed manifold. Okay, so a self map of M is homotopic to a map without fixed point. If and only if the Lefschetz number of F is 0. Usually, the if part is well known, but this says the converse is true, because we are assuming that M is simply connected, right? And he proved this theorem, this fixed point theorem, by redefining the Lefschetz number in terms of by redefining the Lefschetz number in terms of certain obstruction class. And basically, I'm going to follow his proof. I mean, we are going to build up obstruction theory for non-compact manifold and define a sort of Lefschetz number for a self-map of a non-compact manifold. Okay. But to this end, we need to assume the following technical assumption, right? Okay, so a manifold M is uniform if there is an uniformly equicontinuous. Family of diffeomorphisms. Not homeo, not diffeom. Homeo is not nice now. Homeos. Such that each hxy sends x to y. Okay. Of course, for each pair of points xy in M, we have such a homeomorphism. But the point here is that this family must be equicontinuous and uniform. Okay. Right. So for example, if M is a manifold of bounded geometry, and there is an action of a group on M, which is compact. Okay, G is discrete. Then we can prove that M is uniform. Okay. So for example, then if there is a Galois cover over closed manifold N, then M is the total space of this Galois cover, then M is uniform. Okay. Right, to state the main theorem, we have to make things clear about what kind of fixed points we are going to consider. I mean, of course, we consider usual fixed points, but what about the following sequence of points? I mean, now let X be a metric space. And we consider a sequence of points in X and a self-map of X satisfying this condition. Dxn fxn is, say, okay. So if this sequence is convergent, we get a fixed point, usual fixed point. But it's not convergent, we get a kind of fixed point at infinity. Okay, fixed point in the end of this metric space. And since we are considering a non-compact manifold, we want to deal with this kind of sequence too, besides the usual fixed point. And then, so we need the following notion of almost fixed point. Okay. Right. Now, let F be a self-map of a metric space X. And we say that a point X is a C almost fixed point of F for some positive number C if
what are the restrictions on that sequence?
this is the restriction.
Can all the xi's be the same?
Yeah. So yeah, of course we include that kind of case. Right.
I sinned. Sorry.
If all points are the same, it's just a fixed point. Okay. All right. We said that a point X is a C almost fixed point of F if the distance between X and Fx is less than C, right? So if F has no C almost fixed point for any C, then F has no fixed point and no fixed point at infinity. And this is what I want, okay? And I'm gonna express this situation by saying that F has no almost fixed point, okay? I'm not gonna say for all C. Right. Okay, this is the fixed point which we are going to consider. And next, let's set self-map and homotopies, which we are going to deal with. Okay, so Weinberg considered the vector field of unit length. Okay, and its corollary is something a diffeomorphism, which is very close to the identity. But I'm not going to consider diffeomorphisms which are very close to the identity map. I allow a map as somewhat distant from the identity map. But I'm not going to allow any self-map because it's really uncontrollable. So I'm going to put this condition on the self-map of manifold. Okay, so now let's consider a self-map F of a metric space X. And we say that this map is bounded if there is a number R such that dx fx is less than R for any x, any point x. Okay. Of course, even if f is bounded, it's not homotopic to the identity. Okay. For example, if x is compact, any map is bounded. Right. So this is the map which I'm going to consider. And the next one is the homotopies. Okay. Oh, and now let's go back to the Weinberg again. And he considered a vector field with bounded derivative, which means that the vector field, that means that vector field changes not quickly at one point. Okay, so it changes somewhat uniformly. So we're going to consider the uniformly continuous homotopies. Okay. So the deformation by homotopies is deformation by a uniform continuous homotopy or uniform homotopy is somewhat bounded. All right. So with this setting, I can state the main theorem. Right. Now let M be a uniform, simply connected manifold of bounded geometry. Okay. And let F be a self-map of M, which is bounded and uniformly continuous. For such a map F, we can define a variant of Lefschetz number, which we call uniform bounded Lefschetz class, and which detects the fixed points of F, okay, in the following way. F has, okay, now F is uniformly homotopic to a bounded uniformly continuous map. Without almost fixed point. If and only if our uniformly bounded Lefschetz class of F is 0. Okay. And this uniformly Lefschetz uniform bounded Lefschetz class is an element of zeroth uniformly finite homology of M, which is defined by Bloch and Weinberger. And actually, this is very big, infinite dimension in general. Yep.
Is a closed manifold uniformly bounded?
Yep.
I see. Okay, thank you.
Because, the closed manifold is always always have bounded geometry, and usual homeomorphisms sending x to y, hx, y, form a family of equicontinuous uniform family of homeomorphisms. Of course, okay, so if M is closed, this is the classical one of Padel. Right, so let's talk about a little bit about uniformly finite, zeroth uniformly finite homology of M. Okay, So, okay, let's consider again the case of Galois covering over a closed manifold. Then this is isomorphic to the module of coinvariance of L infinity G Z. Okay. So this is a set of bounded function from G to Z. And of course, the G acts on this module by translation, and the module of coinvariance of L infinity G Z is the module of coinvariance with respect to this action. Of course, and this zeroth homology is isomorphic to this big module when G is amenable. And if G is not amenable, this is 0. Right.
So where is M in your coinvariance? So
Okay. So you mean that the M doesn't appear in the...
exactly.
All right. Thank you. That's a very nice question. A uniformly finite homology is actually a quasi-isometry invariant. And G and M are quasi-isometric in this case. So these are the same. Right.
I'm not sure maybe I missed something you said, but when you say continuous map without almost fixed point, you're saying there exists a C such that
Yeah. There is C.
Daisuke,
No.
could you
For
repeat the
any
question?
C, there is
so
no.
for any C there's a
Yeah.
map.
Yeah.
For any C there's a different map.
No. There is a map which has no C almost fixed point for all C.
But how can that be? Because you can only move a point finitely far away.
Mhm.
So there's for every map there's gonna be a C such that there's a C almost fixed.
Yeah, I don't understand.
Or maybe I misunderstood the definition of C almost fixed.
All right. C.
Actually, we need to suppose there are no C almost fixed points for sufficiently small C.
Okay.
This is maybe the correct assumption. Okay.
All right. So this is saying that it has no fixed point and it has no fixed point at infinity. Right. All right. So okay, having this, we have an immediate corollary to this theorem. Okay, let M be the universal cover of a closed manifold with non-amenable pi 1. Okay. Then any self-map of M, a bounded uniformly continuous self-map of M is uniformly homotopic to a bounded uniformly continuous map without almost fixed point. So without fixed point and fixed point at infinity. Right. So if G is amenable, we can't say this, of course, because this uniform bounded Lefschetz class can be non-zero. How much do I have time?
20 minutes.
Okay, thank you. All right, so I'm going to roughly explain how to construct this uniform bounded Lefschetz class, right? So, of course, we need to, of course, as I said, I follow the idea of Fadeo, I mean, defining the Lefschetz number by an obstruction class. But the point here is that we don't have a right cohomology. I mean, right cohomology for obstruction theory. I mean, maybe a naive choice of the cohomology for non-compact manifold should be bounded cohomology, but it's too rigid to control uniform homotopy. So it's not good. So we need to introduce a new cohomology which behaves well with respect to uniform homotopy. All right. Okay, it's based on this well-known result. If M is a manifold of bounded geometry, then it has a triangulation by a uniform simplicial complex. So what is uniform simplicial complex? It is of course, it's a geometric simplicial complex satisfying the following condition. Okay. There is K such that there are at most K simplices around each vertex. Okay. And the second condition is about the metric. It has a piecewise linear metric. With unity adjoints. Okay. Sorry, and not a triangulation, but much better triangulation by Lefschetz. Okay. So what we want for our cohomology is three things. The first one is that it is at least by Lefschetz invariant. The second one is it is uniform homotopy invariance. And the third one is that it behaves well with uniform simplicial complex. Okay. So we come to this definition of uniform bounded cohomology. All right. So we say that now let X be a metric space. We say that a family of singular n simplices in X is uniform, not all the singular n simplices. something or anything is uniform if for any R there is KR such that BRX, which is a ball around X with radius R, meets at most KR of sigma I for any X, for any point X. And it is equicontinuous. Right. Of course, the first condition corresponds to the first condition of the definition of the uniform simplification complex. And the second condition is roughly corresponding to the second one. Okay. And we define a uniform n cochain on X to be an n cochain, which has bounded image for all uniform family of n simplices. Right? Right. So uniform bounded n cochain. Okay, over a pseudo abelian group A under bar is of course, a pseudo abelian group is an abelian group with a specific pseudo metric, and A is the underlying abelian. Right. So is an n cochain U on X such that sup U sigma I is bounded for any uniform family of n simplices. So the usual bounded n cochain requires the boundedness on any family of all n simplices, n singular simplices, but we only require the boundedness for any family of uniform n family of uniform family of n simplices. Now, of course, uniform bounded n cochains form a abelian group, and of course, it forms a cochain complex by the usual coboundary maps. So we can define its cohomology. Which is nothing but the uniform bounded cochain cohomology of X with coefficients in it. Right.
Is that a cohomology theory?
What do you mean by cohomology theory?
Satisfy the axioms?
No, no. Okay, that's a very good question. Actually, what?
They're asking you to repeat the question.
All right. This is natural with respect to not all continuous map, but for effectively proper uniformly continuous map. For example, by Lefschetz homeomorphisms and the inclusions of subspace inclusions. Okay, and it satisfies a sort of excision and the Meyer-Dietrich sequence. So we can consider a sort of cellular cochain complex with this uniform bounded cohomology. Okay, and quite similarly, we can define, sorry, it's cohomology. We can define the uniform bounded homology by using a uniform family of n simplices. And it is also uniform homotopy invariance and natural with respect to effectively proper uniformly continuous map and satisfies excision and Meyer-Beatrice sequence. The important point, so as far as we consider the uniform bounded cohomology and uniform bounded homology, we can identify any manifold of bounded geometry with a uniform simplicial complex. Okay. So for example, if M is oriented, we can define its fundamental class by the sum of all n simplices, oriented n simplices. N is the dimension of n. And actually, we have the following Poincare duality. Of course, we can define the cap product. Yeah. And n is the dimension of n. Z bar is Z with the usual no. Okay, this is very nice. And as I said, we can consider the cellular uniform bounded cellular Cochain cohomology. So for nice CW complexes, we can build up an obstruction theory with it. Right. Namely, we can build up the obstruction theory in the following form. All right. Let's consider the relative fiber bundle. Okay, a pair of fiber bundles over B. And we can define its uniformness by the quick continuity of trivialization, right? Uniform. Okay. Right. So for this uniform relative fiber bundle, we can build up the obstruction theory and in the following form. Okay. There is an obstruction class S, where S is a section, bounded uniformly continuous section of which is and F0. We can keep suitable pseudo-normal on this homotopy group. Right? Sorry? No, these. Thank you. That ON is S is 0 if and only if S is uniformly and vertically homotopic to a section S0 such that S0 of B and my N is in some int epsilon E0. Int epsilon E0 is the union of, the set of points of E such that B epsilon X is in Z. Okay. Of course, we have more concrete information, but the main theorem is like this. So now we apply this obstruction theory to the Fadeno vibration. I mean, the relative version. Here, this is the first projection. This is the relative Fadeno vibration. Of course, delta is the diagonal set. And if M is uniform manifold, this is uniform relative fiber bundle. So we can perform the obstruction theory like this. And now, suppose you have a self-map F. Okay. Then you can find a section SF of this P. Okay. And F has no almost fixed points if and only if SFM is in int epsilon E0 for any epsilon. Okay. So if we define the uniform bounded Lefschetz class by the cap product of ON M cross M minus delta SF with the fundamental class of M, then we get the main theorem. Okay. I mean, if this is 0, then this obstruction class is 0 because we have the Poincare duality. And so if this obstruction class is 0, this holds. And but now this is actually an element of the uniform bounded homology, 0th uniform bounded homology. But we can prove that this is actually isomorphic to uniformly finite homology of introduced by Bloch and Weinberg. Okay. So that's the proof of the main theorem. Okay, to end my talk, I'm gonna tell you what should we do next. Okay. Now we have defined the Lefschetz fixed point, Lefschetz class, but we don't have the trace formula. Right? That's really hard. I mean, because uniform bounded homology or cohomology are generally infinite dimensional. So what is trace? I don't know, but at least the Galois cover case, I think we can get a kind of a trace formula for the LUBF. Okay. And also, I think we can easily extend our result to the coincidence result. I mean, coincidence of two self-maps of M. Okay, so in the fixed point case, this is the coincidence of F and the identity. Right, that's all I want to say. Thank you very much.
Okay, great. So any questions, comments?